Okay, so welcome. This will be the first of our 6th webinar series that we will run, and we will hopefully be doing this every year. That is the plan. And about this time for Australia, we have 6 webinars. We are on the first one today. And the main objective for today would be to pretty much introduce you to our various apps and databases so that you can get a good feeling for what is available in the database. Later webinars in the series would focus on how to work more specifically, for example, with core data so that you can classify your intervals. And then we will have deep dives into Fluvial dominated, wave dominated, and tide dominated environments. Finishing off with a webinar that focuses specifically on how to work with channels. My name is Bojan Vakrolov. I finished my PhD back in 2006 at the University of Texas at Dallas. I then did 3 years as a lecturer at ASP at the University of Adelaide. And since then, I've been working in various iterations on Sedbase and the various apps and databases that are part of the product. So what is Sedbase and what does it contain? It contains a number of apps and databases, as I mentioned. So we have apps that focus specifically, for example, on finding depositional analogues. We have apps for working with and finding fluvial and shallow marine dimensional data, in addition to having apps that help you make interpretations in the subsurface in an uncertainty framework. If you think about the typical reservoir modeling workflow that you're following, doing data analysis, structural modeling, stratigraphic modeling, phases modeling, property modeling, etc., where we fit in is kind of in this stratigraphic model, phases model part of the workflow. More specifically, the main use of Sedbase would be to help you what we can call working out the deterministic portions of models, so things such as figuring out depositional environments, choosing appropriate depositional scenarios, and then obtaining, for example, dimensional data for object models that you can use in your modeling. Now, the project itself started in 2008 at the University of Adelaide. So between 2008 and 2015, it was run as a university-based consortium based in ASP. Since 2015, the project has been run as an independent company, Sedbase. We currently have 4 sponsors, and there were quite a few sponsors back in the day when the price of oil was it was. Now, how do you get to Sedbase? And how do you get to our website? You have to go to our website, which is sedbase.com. Once there, if you have not signed up already, you would press the sign up button. You would go in, you would use your company email. This is important. This is how we actually give you access to go to our private pages. So you would use your company email when you sign up. You would choose your own password. So we don't have access to your passwords. Everything is handled very securely. You would get an email from us, which you would authorize, and then you will be able to go in to our private pages. Once you go in, if you want to get to the Wave Knowledge Base itself, you would click on the orange button on the top. In addition to that, if you're opening things up for the first time, have a look at the page that opens. It has links to some of our documentation pages. It guides you through some of the things that you might want to check out before start using the database. Once you go in, you will then get to the main part of the database. This is the main page where you will be accessing most of our tools. Now, what are the objectives for today's lecture? Kind of the first lecture in our webinar series. So first of all, we want to learn how we can use Sedbase. So what are the various use cases that you can use these tools in practice for your work? We want to learn the nomenclature that the database uses, so that you can most effectively work with it, kind of derive, for example, the data that would be most useful to you. And we would finish off with a live demo, which would be showcasing actually a new addition, a new updated version of an integrated modern app, which you would be seeing for the first time today. So when you work with with Sedbase, we very often recommend following a workflow which is starting off with, for example, whatever data you're working with. So let's say that you have some core data with some wireline data. As a first step, you would always classify your intervals so that you take your information and then you convert it to the language of the knowledge base, if I can use that, so that you work with categories that the database would understand. You can then start looking at things such as analogues. We have modern analogues, ancient analogues, etc. We have additional tools which will then allow you to make predictions about what might be happening in your interval away from your well locations. So we have a number of predict modules that help you do this. And as a last step, once you have characterized an environment, once you have built kind of a conceptual model that works for your field, you can go in and you can start getting the relevant dimensional data. So back to the main part of the main page of Wave Knowledge Base, something else which is quite important is that a lot of our nomenclature, and we will be talking about our nomenclature in the second part of the lecture, is based on a hierarchical framework. So every time you use, for example, you try to find data, you will be able to find data at the right architectural level. So we can start off at the scale of sequence stratigraphy. We then have parasequences, depositional systems, delta lobes, phases associations, heterogeneity. So this is an important thing to understand right from the get-go. The database is based on a hierarchical framework, so you can always focus at the right level of data depending on the type of question that you're trying to answer. So if you're working, let's say, in a gas field and you're a bit less interested in kind of high-level heterogeneities, you might be able to go to the correct level in terms of data so that you can more effectively work with your reservoirs. So we mentioned these 4 parts of the workflow: classify, find analogs, predict architecture, and find geospatial data. Let us very quickly introduce you what we mean by classify. Now, the next webinar that we will be having in 2 weeks from now would be entirely focused on this subject. So we will spend a whole lot of time kind of going over our various modules that we have available to you that help you classify core. But just to give you a visual of some of the things that you can do, for example, imagine that you're working in a chord interval, and the question that you're trying to address is what type of depositional environment, what type of phases association is this particular core interval meant to represent? Well, for example, we have one tool, one app which is available in which you can start describing kind of physical characteristics of the core. So in this case, you're saying the interval is coarsening upwards. It has a heterolithic and a sandstone dominated portion. We then have an interactive app where you can physically click on the various physical structures that you can observe in the interval, and you can also give their percentages. So this is your input in this case, observations that you're making in core. We have an integrated physical structure atlas as part of this app, so you can directly, even in the core store, if you like to, you can go in, you can look at images of what we think some of the physical structures that you're observing look like. You do this, you characterize your data, and then you get a set of results. So we have kind of big tables in the background, rule-based tables, which gives you possible sets of interpretations based on the observation that you just made. We also have an additional module which focuses on trace fossils, basically ichnology. We worked with James McEachern, a very well-known ichnologist, as part of this work. So you can actually go in, you can describe trace fossils if this is something that you can do. Once again, we have an integrated atlas as part of this. So we have an integrated trace fossil atlas. So in this case, we've characterized the physical structures, the trace fossils, and you end up with a final set of possible results, possible interpretations of your core interval, which you can then start using as the basis for the type of data that you might want to get as part of the workflow. So this was step 1. The second step is finding analogs. Now we have quite a few different types of analogs we can work with. the most useful parts of the data that we have deals with modern analogs. So we have this modern deltaic coastline interactive atlas, for example. You would get to see all of this in the demo at the end of today's presentation. Now, this is based on a major data collection effort since 2015. So what we did, we went around the world and we mapped a whole lot of systems, basically most of the systems that can be mapped in detail. Mapping is geomorphologically based, so we have 320 systems at the moment, roughly, in the database. So you can query these, you can learn from them, you can get various characteristics of these. So what do these systems look like? This is a typical view of a system in the database. So this is a delta. You see different colors. What is shown in orange, for example, are scroll bars. So in this case, you can get a good feeling for what the various, for example, point bars are doing in the system. We have active and abandoned channels also shown in blue. In white, we have beach ridges. We also have bathymetric contours. So the point is that you can almost think of this as interpreted seismic. So when you go in and look at a modern analog, we have this interpretation which is superimposed on it so that you can better understand what is happening in the system, how it evolved, what type of geomorphological elements are building it. In addition to that, we have mouth bar deposits that's mapped in front. So the point is that we have many systems which have been mapped in fair bit of detail, and these are great kind of sources of information for getting a good feeling for what is the natural variability of these types of systems in the real world. Once we start focusing on fluvial dominated, wave dominated, and tide dominated systems in the series, we will be using a lot of these maps to in essence learn as much as we can about these systems, so that once you start building conceptual models in the subsurface, you make more reasonable assumptions. These systems are from around the world. So the typical workflow that you would be following in the database once we get there and once we start using these apps is that we would always have this filter view on the left-hand side, a map view on the right-hand side, which shows you what systems are currently being active. You would be able to filter and select types of systems based on criteria that are appropriate for your subsurface scenario. You will then be able to view a particular analog in detail, and you will be able to study from it. That is kind of the idea. In addition, each system has a number of metadata points, kind of information associated with it. So for each system, we know what the process at the coastline is. We know what the tectonic setting is. We know what the receiving water basin setting is. We have information on tidal ranges. We have information on distances to shelf edges, channel gradient, etc. So the point is that you can, based on the subsurface field that you're working in, you can select the most appropriate systems in terms of analogs, and then you can view examples of these directly in the database. In addition to that, every time we have a numeric field in all of the modules in the database, you can also view directly chart data, things such as histograms and cross plots, so you can very quickly assess both visually and in terms of numerical data what types of systems you're dealing with. So I'm going through this fairly quickly. You would get to see how all of this works in the live demo at the end of the lecture. So we've classified our interval. We've looked at analogs. So at this stage, we should have some good idea of conceptually of what our reservoir might look like in terms of architecture. Now, something else which you can then do is use one of our predict architecture modules. And what these things do is that they help you think about what other types of architectural units you might want to think about in your conceptual model, kind of in your framework that you're using, which might not have been directly penetrated, let's say, by a well. So oil and gas fields are three-dimensional structures. They're typically penetrated by by not too many wells, which sample a very small part of the reservoir. And very often in the real world, we might be sampling one part of a depositional system and not sampling another part of a depositional system, which might end up being important. So one thing that you can do with these predict modules is that you can tell the database what types of units you have identified. In this case, we have identified an FT mouth bar. So this is a fluvial dominated tide influenced mouth bar deposit. This is what we have observed in core. And then you can use this app to help you, first of all, tell you what types of parent depositional environments can be associated with what you just observed. And again, think of hierarchies in this case. So our initial input is on this element complex level, our facies association level. This prediction that you can see on top is lower down. This is basically a type of a parent environment which can house the facies association that we just identified. So this is the first thing that these modules can do. The other thing that these modules can then do is actually tell you what types of siblings can occur in the same interval which you are not penetrating. So in this case, you're being told that there might be other types of mouth bar deposits, there might be tidal flats, there might be different types of channels. Again, the point here is this app is not giving you answers, but it is making suggestions of things which you might not have thought about in terms of architectural complexity, which might be present in the subsurface and which you might want to capture in your modeling potentially. So this is what we mean when we say predict, kind of getting away from the known data points and giving you suggestions of things that you might want to consider in the unknown part of the field. The very last thing that you can then do is find geospatial data. Now, in this case, we have a number of atlases and modules that you can use. So we have geospatial data on channel belts, geospatial data on channels, data on mouth bars. We also have some ancient data as well based on interpreted cross sections from well-known outcrops. So let us see what dimensional data in the database might look like and how you can access it. So let us start off with looking at fluvial channel belts. Now, very often when you work with channelized intervals in the subsurface, it is the channel belt as the most important unit that you want to be working with. The channel belt, if you want to define what a channel belt is, it's the sediment which is left behind after a channel has been allowed to migrate for a while. So we are not looking at an active channel and its shape. We're looking at the shape of all of the deposits that have been left behind for the duration of when this channel was active. So we have quite a few channel belts in the database. We have something like 2,600 of them from 32 systems. We came up with kind of a semi-automated way to extract the parameters of the shape of channel belts so that we can input them in the database and then you can query them. Also, channel belts are linked to parent systems. Once we get to the live part of the demo, you'll be able to see that we will be able to look at, let's say, a system, characterize it, and then look at the channel belts which are associated with that parent system so that we can see how, for example, channel belt dimensions vary if you change the dominant process at the coastline. It turns out that all of these things are important. So what do we mean by channel belts? When we map channel belts, we always start with our geomorphological maps. Now, this is a zoomed portion from the Rio de la Plata system in South America. In this case, we have channels and scroll bars mapped. We are using these maps to then outline a shape of a channel belt. Okay, so in this case, the channel belt is shown in yellow. Okay, so this is the type of shape that we would be working with the channel belt database. Now we do this for all channel belts that we can map. And again, we've gone around the world and we have tried to map as many of these things as we've been able to. So we end up with very irregular looking shapes very often. We do this regionally. Okay, and we have done this in 32 different systems around the world. The next thing that we did was to take these polygons, these shapes of channel belts, and then using scripts, trying to, for example, fit a line through the center of these polygons. Once we fit in this center line, we can start looking at inflection points. So we know the positions of this, and then we can start looking, for example, as how is the thickness of the channel belt varying relative to this center line? What is the distance between inflection points? Something else that we can also look at is we can find local minima of thickness. These are these red lines, if you can see them. We can also get distances between them. So the point is that we have a way of characterizing this very complex shape so that we can make some sense of it. In addition to that, we have these yellow areas in this case. So these are anomalously thick portions of the channel belt. We also have a way of differentiating these from the parts of the channel belt which are more kind of regularly shaped. So the point is that we have collected a whole lot of dimensional data based on these polygons, and all of this data is available in the modules and can be used to better characterize dimensional data. So to access the channel belt data, you'll go to one of our atlases. Again, we have filters on the left-hand side, a live map view on the right-hand side. What we are doing now is we are about to show a histogram of the sinuosities of all channel belts in the database. We do this, we can narrow down the ranges of the histogram if we like to. So very quickly, we're actually studying what is the variability of sinuosities of these channel belt objects in the entire database. And one thing that, for example, is quite interesting in this entire data set is that you can see that most of the channel belts in the database are fairly straight. We can see the distribution of sinuosity, so you can see that the vast majority of these are close to 1. So channel belts tend to be straight features for the most part. Now they can be sinuous as well, but they almost never look like this. So very often when we, for example, use the channel kind of object modeling features, let's say in Petrel, very often we draw these highly sinuous shapes. And again, our data is suggesting that since really what you want to describe in a model is the channel belt, not the channel, most channels tend to be straighter than these highly sinuous features, which, for example, are shown in the Petrel study notes. Okay. So these are some of the practical ways in which you can use these data to get a feeling for what tends to occur in the real world. Something else which is very powerful is once you have selected an analog or a set of analogs that you're happy with that represent your particular subsurface scenario, you can actually focusing on this, and then you can, for example, get channel belts from a particular system or a set of particular systems that best fit your data. So in this case, we have focused on a single system. So this is a Fluvial dominated delta, the Volga system in the Caspian Sea. And we can very easily, for example, study what is the sinuosities of channel belts in this entire system. How is the median width varying in this entire system? So very quickly, we are getting values of, for example, the median sinuosity in the Volga is close to 1. It's a bit over 1. You can see what the spread is. The median channel belt width is about 500 meters. Again, those are things that you can directly start inputting into your object modeling if this is what you're doing. Again, the nice kind of benefit of using this approach is that you can very easily use channel belts not only for dimensional data but also as analogs. We have mapped these things, we know what they look like. So this is just a visual of a conceptual model that was based in an interval in the Cooper Basin, based on the OP system. Well, we have the actual OP system mapped. Again, the point is that you can use our geomorphological maps to help you make decisions about, what types of architecture do you want to include in your subsurface 3D modeling. You can see that, for example, that there is a lot more smaller channel belts on the right than what was initially used in the conceptual model on the left. So again, this is just a very quick view through our channel belts. My objective for this lecture is to give you a flavor of what is out there. So we are not going into any details in anything. We will be doing this in the upcoming webinar. So we will get plenty of time playing around with all of these things. But at the moment, I want us to just get a feeling for what type of data is available in the database and how you can potentially use it in subsurface scenarios. So the next data set that we have is fluvial channels. Now this is data which is coming from active channels. So again, note the difference between a channel and a channel belt. The channel belt is the body of sediment that gets left behind after a channel is allowed to migrate for a while. The channel database itself is looking at the shape of the actual channels. So it is very important to understand what is the difference between a channel and a channel belt once you start using dimensional data in the database. So this has been a fairly big effort in terms of data collection. So we have something like close to 90,000 points with data. At each location, we have measured for different things. All of this work was done by hand. For example, we have over 12,000 points with depth information of active channels. So very often we have some idea of how deep channels are. The reason why we worry about channel depth is because this in turn would scale to the thickness of channel belts deposits vertically that would be preserved after these active channels have been allowed to migrate for a while. So a fairly big data set. Many basins around the world have been mapped. So this is, for example, a regional view of the Amazon basin. Everything that you see in yellow in this case is a area with measurements. If you zoom in, you can see what actually has been measured. So in this case, you can see this curving shape of the active channel. So what we do is every time we have an inflection point, so a change in direction of curvature, we would put in a width measurement, basically. So this is what these little yellow lines are. And then we would also make additional measurements based on these locations that I would show you in just a little bit. But the point is that we have a lot of data from many channels all around the world. So if you actually view kind of a global map of all of our channel point data that has been collected, you can see that we have data from all around the world. A lot of data in the, for example, in the Up Basin, Amazon Basin, and many data points again around the world, mostly focusing on our systems that we started off with. So very often we would have channel data from the same systems that we have already categorized it in terms of analogues. So you can actually relate observations at the system level to observations at the channel level. So if we go to one system, here is one. We are kind of zooming into an area. Once again, you get this view and you get a feeling for where the points are. So points are placed at positions of change in curvature of the channel. If we zoom in further, you can actually see what has been measured. So at every location, this would be a point. At each point, we would measure the width locally here of the active channel. We will measure the direct distance between this point and the next point adjacent to it in the same channel. We call this LD. We also measure the long channel distance. We call this LC. And we also measure the offset between the two lines, which is called A. Now, again, getting a feeling for those things is important because you can actually go in the database and you can query channel points based on these variables. So if you're interested in, what is the sinuosity of a channel of a given width with a given LD measurement, you can get this type of data. So at each location point, apart from these measurements that I mentioned, we also have a script which is telling us what the elevation of this point is above sea level. And we also know how far a given point is from the channel all the way at the channel mouth. So we can actually query for data based on distances from the coastline. So again, all of this is allowing you to very narrowly focus on the type of area that you're interested in. In quite a few places, we also have where this data is available. We also have maximum depth of data. So if we have a channel stretch, which depth information, which is coming from a website called Navionics, we would look at the maximum depth of scour that we observe anywhere in this channel stretch, and this is what we are going to record in terms of depth. The idea is that the maximum depth of scour would most easily be related to the thickness of the channel belt, which would ultimately be preserved. So what are some of the ways in which you can use this channel data? Well, one thing that, for example, you can very easily do where you have the data available is imagine that you have a seismic channel which you have been able to observe. Well, one thing that you can do is you can actually make measurements of this seismic channel. This is an example of one. And then you can find very similar looking modern channels which occur at exactly the same scale and have a very similar kind of sinuosities and shapes associated with it. Yeah, the reason why this is useful is because once again, we go from the ancient to what modern rivers of the same size and features tend to occur in. So we can then study how deep those rivers are, what types of depositional environments that they tend to be associated with how large they are, what is their drainage basin. All of these are useful things to then know and apply for in the subsurface. Something else that you can then do is, for example, if you have some idea of the dimensions of your channels in the subsurface, you can very easily find examples of these things in the modern. So again, you use your ancient data as an input, and then you see many examples in the modern as an output. Again, getting a feeling for the sizes of channels that you might be dealing with. Now, in this case, we've run a query. And you might not be able to see this too well, but you will notice that a lot of the channels, based on the query that we have run, you're looking at these small red points, they're associated with smaller channels in this larger system. So sometimes, for example, you might be observing smaller channels, but there might also be bigger channels which are part of the same system which you have not sampled. And again, this is why these modern analogs can be useful, because they can get you to think about some such things. One way in which you can very directly use, again, the ancient data, the modern data sets associated with ancient data is, imagine that you have a log. You estimate the thickness of channel belts based on log signatures. Okay, so you're looking at the log motif here, and so you estimate a thickness. In this case, we estimated the channel body thickness is about 4 meters. Well, once again, we can go in and we can start looking at, okay, show me examples of active modern channels which have this depth associated with them. So this is, again, an example of one system which has 4 meter thick channels, 4 meter deep channels as a part of it. Now, this is a fluvial dominated interval, which is occurring in a valley. If in the subsurface, in the interval that you're working with, if you think that this is a fluvial dominated interval, which is occurring in such a valley setting, you can directly start looking at this modern analog and start thinking about, what type of architecture does it likely have, what is the channel variability, channel belt variability, etc., etc. So this is how you can use all of these things so that you can ultimately refine the conceptual models that you put in as part of your workflow. A few more examples. Again, some seismic data that we can use. So very often in seismic, we can figure out what the shape of a given channel is. So in this case, we do this on both examples. So this is the channel belt. this entire body, but we can use the channel belt to actually infer what the shape of the channel is. The moment we have a shape, we have measurements that we can then apply. The same thing here. And again, what you would do is you would get these points, you will get the direct and the long channel distances between them. You can put those things in the database, and then, for example, you can get measurements of, what is the width of such a channel typically that has these given sizes. So again, the idea is how can we use observations in seismic to say something about the entire channel belt and the channel which is forming it, which might be below seismic resolution. So again, quite a few different things that you can do with these data sets. And again, this is how these measurements would work. So we talked about channel belts, we talked about channels. Let us say a few words about mouth bars. Now, when we talk about mouth bars, we're talking about a data set which again was based on modern data. Now, to give you a good feeling for what was measured and why it was measured, let us use this diagram, which is comparing an ancient case study that was done as part of the WAVE consortium at the University of Adelaide, which is showing these mouth bar send lenses, which again, we went in and mapped in a fair bit of detail. So you can see that for fairly small distances, this is 1 kilometer for scale. So we're looking at something like 8-9 kilometers in terms of strike extent, something about 10 meters of thickness, just to give you a feeling for the dimensions of what we're looking at. So in this very small area, we can see that there is a lot of heterogeneity and complexity which is being involved. Now, if we look at the modern example from a very similar environment, now this comes from the Mitchell River Delta, which is another area that we did work in as part of the WAVE consortium. If we actually go in and start mapping in a fair bit of detail how the active mouth bars of these systems are building over time, you will actually see that they're forming very similar scale features to what we are observing in the ancient. So when we talk about the mouth bar database, in this case, we are referring to going around the world and trying to map systems such as this so that we can get a good feeling for how these active mouth bars are building over time, so that we can take the lessons and again apply them to the subsurface. So we have identified 632 mouth bars which have been done in this way, again with global distribution. So I've gone in and I have mapped all mouth bars that I've been able to find. You can see examples of the mouth bars in yellow again on this map. So you can see what was done. Basically, I went around the world. I tried to find suitable candidates for these geobodies which can be mapped. If we zoom in, we can see that basically a lot of these maps are associated with channels which are actively supplying sediment to them and allowing these geobodies to build over time. Now, let us see how exactly those things were mapped. Again, it is very important for you to get a good feeling for what type of data is actually available and what it represents. So we would go into an area. We would use historical Google Earth imagery. So typically we would go back to 84. So at each location, for each mouth bar, we would look at historical imagery, and then we would map these breaker zones. Now, what these things are is those are waves which are breaking in the very shallow portion in front of the mouth bar. So we get this shape, and basically what this shape is telling us, it is giving us directly the shape of the shallow portion of the mouth bar sand body, which is in front of the channel at this particular time. And one thing which we can then do is we can go through these things through time. So in this case, we start at 87 and we make our way to 2016. So what we do is we map the location where the mouth bar is at any one time, the actual kind of most active sedimentation point along it in 3 dimensions. And then we end up getting a map like this, which is showing us basically where are the active portions of this mouth bar deposit over 30 years. This is what has then been mapped, again, over 600 times around the world. We can then build polygons around those things, and then we can get a good feeling for the dimensions of these bodies. Now, what is very important to note and to understand when you're using this database is that this is only showing you the shallow portion of the mouth bar. So in 3 dimensions, all these things will extend a bit further, but they do this in a predictable way. And again, you can very much use the top portion of the mouth bar as a very useful kind of guide to what the entire feature does in 3 dimensions. So what do we measure? So we would go in, we end up having these polygons. So we would get a strike extent, a dip extent of each polygon. We also have measurements of, for example, what is the size of the channel which is feeding these channel belts, these mouth bar deposits. We also make measurements to water depth some distance seaward from the mouth bar. Now, everywhere I've looked around the world, for the most part, a mouth bar geobody would die down by the time we are, let's say, 5 or 10 kilometers seaward from the seaward portion of the mouth bar. So if we're right here, in the vast majority of cases, this entire deposit would have completely died down by the time we are, let's say, 10 kilometers from this location. Very often they would have died down 5 kilometers in front of this location. And what we then do is we get the local depth of water, this distance seaward from the mouth bar, and what this is telling us is this is giving us a good idea as to the water depth in which this entire mouth bar body is prograding into. So if this number over here is, let's say, 5 meters, this is telling us that the thickness of the entire mouth bar package which is prograding will be 5 meters. If this depth is, let's say, 50 meters, it will be telling us that this mouth bar package is forming a fairly thick coarsening upward succession. Okay, so the point is that we have measured a whole lot of data associated with these polygons, which we can then use, kind of get histograms from, get cross plots from. Just to give you a feeling for why this type of data should be trustworthy. Again, everywhere around the world where I've looked and where I can get bathymetric data which is showing you the shapes of these mouth bar deposits, the shapes look very similar. So notice what we are measuring. In this case, we are describing this shallow portion of the mouth bar. In 3 dimensions, the mouth bar will extend further, so it will probably get down to here. And as you can see, there is a 3-dimensional body, but the 3-dimensional body is still following the shape of its shallowest portion. So what are then some of the things which, once we go in and use our mouth bar interactive atlas, what are some of the things that we can, for example, get? Well, one thing that we can study is what is the effect of tides on mouth bar dimensions. Now, this is very important because, again, if you're working in a subsurface setting which was affected by tides, and if you think that you're dealing with mouth bars, it is very useful to know whether these tides have some influence on the shapes of geobodies you would expect to get. So in this case, what we've done is we actually have a tidal range filter. So in this case, we've told the database, show us the strike extent of mouth bars from settings which are influenced by low tidal energy. Okay, so basically micro tidal settings. And then we get dimensions. We can see that the median value in this case is about 3 kilometers. So under micro tidal conditions, based on our entire data set, the median strike extent of the top portion of a mouth bar is 3 kilometers. Now, if we were to then do the same exercise, but looking at systems which are strongly tide influenced, in this case, we're looking at tidal ranges which are between 3 and 6 meters, we can see that the width, the median strike extent of mouth bars has increased. So the more the tights, the bigger the mouth bar bodies tend to get. So something else which is also fairly interesting is doing the same exercise, but now looking at the distances between mouth bar bodies, kind of adjacent along the same coastline. And here the difference is quite striking. In microtidal settings, the median distance between two adjacent mouth bars is 12 kilometers. Again, this is bigger than the size of most oil and gas fields. Whereas if we're in a tidal setting, the median distance is only about 4.5 kilometers, right? So chances are that if you have one mouth bar in your model, there would be a second one as part of the same field somewhere. And so again, all of these are useful things to think about, mostly when you're building the conceptual models before you start kind of building proper 3D models to get a good feeling for what are the typical size of things, what types of geobodies might be present there, etc., etc. Okay, we also have some ancient data. Now, this was data that was collected something like 10 years ago. The plan for the project moving forward is to quite heavily go back into ancient data and collect it in a better way than we initially did. But nonetheless, we do have ancient data there. The ancient analog data is coming from well-studied outcrops. So we only go to areas which have been studied quite extensively. The data is collected in a hierarchical fashion, so we know what a facies association within a depositional environment within a parasequence is in all cases. The other thing that should be noted about these ancient data sets is that all data sets have been color coded in exactly the same way. So you can very easily actually compare and contrast different cross sections from different areas which have been redrafted. And again, the point here is to be able to use those things as analogs and to make sure that you understand what exactly has been mapped. So in all cases, we have taken an original case study, we have reinterpreted it based on wave terminology. So all of these case studies use the same terminology in these data sets so that you can very easily compare them and contrast them. You should compare this to what typically happens in the real world, where you have a case study done by different workers using different terminologies. One person would call something a wave-dominated delta. Another person would call exactly the same thing a wave-dominated parasequence. It is very difficult, and you have to spend a fair bit of kind of detailed studying the actual outcrop case study in this case to get a feeling for what exactly was mapped, what each author named each unit. So in this case, for the data sets included in our databases, this work has been done for you. So again, be aware that this is some data which is available as well. And much more of this would be done in the next couple of years. Okay, so this is probably a good time to take a brief break. What we would do in the remainder of today's webinar, the next topic of today would be understanding the language of the database. So I want to make sure that we understand what exactly is being mapped, what we are naming things, so that when you start looking for data in the database, you know exactly what scale of data you're looking at. Is it a facies association or is it part of a larger scale depositional system? And what the various codes and names that are actually used throughout the database mean in practice. So what I suggest now is that we take a brief break, just as a refresher, and then we reconvene back at basically the top of the hour in 8 minutes. After this part of the lecture, we would finish off with a live demo. Now, I still have not figured out if we have a direct communication back. So can somebody try to raise their hand to see if there is actually a way of getting you to ask questions?
Can you hear me at all?
Oh, I can hear you now.
Okay.
So it all seems to be working great. Okay. I thought that I set the webinar up so that mics are open to everybody, but it sounds like they are. So all seems to be working. Okay, so let us get back then in 7 minutes, and we would continue with the second part of the webinar, unless anybody has some questions at the moment that they want to ask at this time.
Yeah, can I just ask a question?
Yeah.
In terms of your modern depositional systems, do you take into account the fact that we're sort of basically in a transgressive systems at the moment, or even still stand? Do you take that into account when you're looking at your models, and it may not actually reflect times where we've got, you know, falling sea level conditions?
Yeah, so we do. And again, this is data that the ultimate goal is for us to make better conceptual models in the subsurface. So even when we're looking at transgressive settings, there is a lot to learn from these systems. Most of the systems that we mapped are in fact regressive, at least locally, because this is where we tend to see the best geomorphology in a way. So my answer to that is, yeah, this is something we should be mindful of. It can be handled with care. It should be thought about, but there is still a lot of useful lessons. So for example, if you're looking at mouth bar architecture, kind of at the facies association scale, chances are that it would not be fundamentally different depending on the particular setting. So variables such as the size of the river, you know, the water depth that it's building into, et cetera, are, if they are similar in an ancient setting and a modern setting, chances are that they would leave the same types of architecture units behind. But having said that, again, this is something to worry about, think about. But again, the point is that there is a lot of useful information in these modern data sets, and I think that it's a real bad idea to just ignore them because they might be different from an ancient setting.
Yeah, no, I wasn't saying ignore it, because there is a lot of useful information. Yeah, it's just like, yeah, just be aware that we're in a particular setting at the moment. So and the other thing is,
go ahead.
Sorry, the other thing is the time element. Is there any capacity to incorporate the amount of time that these deposits are being deposited under into your models?
Yeah,
like in the modern setting and also some of the ancient ones.
Yes, so in the modern setting, this has not been, well, it has been done in part in some of our case studies. So we have some information on, for example, how long does it take for, let's say, a channel on a delta to avulse and form a new delta lobe. So most of our modern examples have been built in about 6,000 years. So if you study them and if you can get a feeling for how many delta lobes they're made up of, you can come up with some timing on these features. Now, this is not something which is actively input in the database at the moment. In all honesty, and it's probably a good idea to add that information, but it's definitely something which it is known for many of the systems in the database, and it can be effectively guessed for many more.
Yeah, I was thinking, particularly when we're studying ancient examples, and we may be looking at systems, and we're looking at hundreds of thousands of years to even a million-year type systems. Yet we can see such dynamic change over, like, even that 30-year period, or even between the last 10, 20,000 years. So, I was wondering if anyone had started to build a time component into the database.
Yes, so basically a lot of the deposition that occurs on the scale of the whole scene does also occur in the ancient. So that mouth bar example that I showed you, I'm fairly sure that the ancient cross section that we were looking at was probably deposited in a fairly 100 years, maybe a couple of 100 years, maybe. So very comparable time scale. So in the ancient, a lot of the time gaps are at key surfaces. So the rates of deposition are similar, I would probably argue. So very often in the ancient, we might look at an entire outcrop which may have been deposited in a fairly short amount of time, but huge amounts of time would be represented kind of at the surfaces, at the tops and bottoms of these intervals. But again, all things that we should definitely think about. In this case, we have a lot of data on what deposition occurs over scales of hundreds to several thousand years. And this is the key kind of take-home messages that we should be taking from the modern data sets. If you're interested on longer time scales, how are parasequences building in a basin, you very much have to look at ancient data.
Yeah,
as
no,
your
that's
main
good.
source of
I
information. Yeah.
think what you're doing is great. It's really good to have that all into one place, and yeah, to have all that data is great.
Yeah. Perfect.
Thanks.
Okay, so let us reconvene back in a couple of minutes, and then we'll kind of move on to the next topic of the webinar. Okay, so let us continue. So far I gave you a bit of an overview of the main parts of Sedbase. As you can see, it has quite a few different apps and databases that you can use. Now, this is something which has been built since 2009, so a lot of work has gone over the years, and the package has grown, as you can imagine. Now, one thing that became very obvious very early on in the project was that initially, when we started the WAVE consortium, we very quickly figured out that in order to effectively deal with heterogeneity in shallow marine systems, we needed a way of effectively describing things. So initially we started building a database, and we very quickly realized that different workers use different names for the same features, the same names for different features. Everything becomes very confusing. And because of that, we ended up being forced to come up with a nomenclature scheme which effectively deals with different hierarchical levels in a shallow marine setting, so that we can apply one set of names for what occurs at the facies association level, which you tend to observe in core, versus what occurs on original depositional setting. So this is why understanding the language of the database is fairly important. So to illustrate some of the problems, in this case, you have a couple of systems from our database. We have the Irrawaddy Delta on the left, the Danube Delta on the right. Both of these deltas are fed by rivers, which are somewhat similar. Both of them are examples of big rivers, kind of continental scale, very low gradient. In both cases, we can see point bars forming. We have a distributive pattern forming. So if you look at kind of the more landward part of these systems, that they have many similarities. And yet, if you go in at the shoreline, the world really changes. The Irrawaddy Delta is a tide-dominated delta. The Danube Delta is a wave and fluvial-dominated delta, depending on which part of the system you're looking at it. But the point is that there is this key thing in shallow marine systems, which is the process at the shoreline, which is fundamentally capable of redistributing sediment depending on what it is. So from the very beginning, it has been obvious that to effectively describe shallow marine systems, you do have to worry about process variability in them. Now, the example that I just gave you was on regional scale, but exactly the same thing happens on more local scale. In this case, we're looking at two wave-dominated coastlines. This is the Nayarit coastline in Mexico. This is the most famous kind of modern strand plane analog in the world. This is an example from the Pacific coast of Colombia. In both cases, the shoreline is straight, so everybody would call those things wave-dominated. But if you actually go in this case, we've gone in and we've mapped mouth bars. You can see that in the bottom example, there is a lot of those kind of mouth bar packages associated with the architecture. The bottom system is wave-dominated, but it also has strong tides with it. So we have about 3.5 meters of tides, which are forcing all of the channels which are occurring in this area to start forming these mouth bar deposits. It keeps the channels open, they grow over time. The point is that we have added a second process, tides, and we have fundamentally changed the architecture of the system. So just visually, you can see that these mouth bar deposits are forming something like 50% of most likely the architecture of the system. So ignoring them would be quite problematic. Something else that we should be very mindful of when we work in the subsurface. Now, all of us know this, but I think that it's important as a reminder. Very often what we do suffers from kind of the ancient parable of the blind man and the elephant, where a number of blind men go and touch different parts of an elephant and they misinterpret it based on their local information. So somebody would touch the ear and they would say, oh, that's a rock. Somebody would, touch the leg and they would say, oh, that's a tree. Now we do exactly the same thing in the subsurface, and this is why having nomenclature is very useful, so that we know that what we observe on local scale may not necessarily reflect what occurs on a regional scale. In this case, we're looking at one of our geomorphological maps of the Danube delta. Imagine that you have a field which captures two parts of two different delta lobes in the Danube. One of them is wave-dominated, the other one is more fluvial-dominated. Very often in the subsurface, we might have a single core that penetrates one of these wells. In this case, we would look at the core. We would say, oh, this looks like a fluvial-dominated system. I know what the fluvial-dominated system looks like. You would go to the Mississippi as an analog, and you would completely ignore that a large part of your field might resemble a shore face. On the other hand, if your core happens to penetrate the wave-dominated portion of the system, it is very easy for you to misinterpret the entire system as a regional strand plane. And the point is that in both cases, these things are wrong. And having nomenclature which allows you to jump between local scale and more regional scale becomes very useful for that, because if you use the wave knowledge base, and if you interpret something as wave-dominated, we would always tell you, wait a minute, it is possible that this is a regional kind of strand plane deposit, but it is also possible that this is part of a mixed influence delta, which might have other stuff in it, right? So this is why being able to work with hierarchies is very practically useful in the subsurface. So let's just do a bit of a review of wave, tide, and fluvial processes on shallow marine systems before we actually go in and see how we name things. Now, the classical way of describing deltas is to subdivide it into wave-dominated, fluvial-dominated, and tide-dominated. Okay, and somewhat ignore the secondary and tertiary processes that occur in systems. Now, there are many examples of systems which are end-member, fluvial, wave, or tide-dominated. Here are a few examples of this. So this is a fluvial dominated delta, which has almost no waves impacting it, which has no tides impacting it. There are examples in nature like this. But more often than not, we are dealing with systems which are mixed influence. So if we look at our databases, you would find examples of n-member fluvial dominated systems, but one thing that you will very quickly realize is that there is not too many of them, and they tend to occur in unusual settings, like very protected inland seas, or a little bayhead delta building in a lagoon, something like that. So typically we are dealing with more than one process. Very often we are dealing with three processes. So many systems are affected by waves, tides, and fluvial at the same time. And this is where things become very complicated. Heterogeneities become a very big deal on many scales related to many different architecture units. So one thing that which again became very obvious early on in the project is that we needed a way to actually kind of assign those things names. So we came up with these codes. For example, we have WFT, WTF. So what we went in as the first step is we said, let us codify the process. So in the database, let us make sure that every time we refer to a process, we are specific about what it is. So when we call something an F, this stands for fluvial dominated, but this is also telling us that there is no waves or tides as part of this system. When we call something TFW, we are saying that this is a tide dominated system, which is also affected by fluvial and which is also affected by wave in that order. So we have these 15 process categories. You will be seeing those things throughout the database in all modules. So if there is one thing that you have to kind of get out from today's webinar is a feeling for what these codes mean. We would be using them throughout the entire webinar series, so you'll get to see them many, many times. But again, this is a very important point to understand, is that we want to be very specific about process, because an F system can be very different from an FT system. A lot more complexities can occur if you add tides to a system, even though it remains fluvial dominated. So this is process. So we have these 15 categories, but there is additional complexities that we need to account for. Again, let us look at a few examples of our analogs that illustrate what the issues are. This is an analog from something that we call the Frontera system. So this is in the southern part, in Mexico, in the southern part of the Gulf of Mexico, a very beautiful wave-dominated delta. But what is interesting is that if you actually look at this system regionally, there is very big process changes that occur inside the same parasequence, if you want to use this term. So notice this sharp barrier over here. Now, this was actually an old barrier island at this location, but in this case, when I say barrier, I mean like a boundary in process. So everything seaward from that boundary is very much wave dominated, textbook strand plane, continuous shore face, you produce it, you don't have to worry about it. Everything behind it is, we are in a lagoon with mouth bars, channels cutting through them, a lot of heterogeneities and complexities behind that one feature. So the point is that the same system can have very different parts of it. And one thing that we realized quite early on is that we needed a robust way to actually assign names to those things. So we don't want to lump the entire unit and call it a single parasequence. We need to be able to differentiate the fluvial dominated portion behind the barrier island from the wave dominated portion seaward from the barrier island. Another issue, very often when we look at analogs and when we describe them in terms of process, and again, we've been doing this since the 70s a whole lot. So we will talk about these fluvial dominated deltas. Well, if you look at the literature, kind of a couple of quite famous examples of fluvial dominated deltas is the Atchafalaya Delta. Now, this is a tiny little thing, which is an offshoot from the Mississippi Delta. It's actively growing in real time in the US, in Texas. Many people, in Louisiana, many people are easily studying it. So there are many papers written on the Atchafalaya Delta, which is fluvial dominated. You also have the Volga Delta, which is fluvial dominated. The issue is that in both of these systems, if you actually look at architecture, you can see that the Volga delta is occurring on a very different architectural scale than the Atchafalaya delta. And in fact, there are features, parts of the Volga delta, which are very similar to the present-day Atchafalaya, which are built in 50 years. And then if we actually want to compare the Volga Delta, we are much better off actually comparing it to the entire regional Mississippi Delta complex, in essence. So again, there is this notion of we can describe something in terms of a process, but we have to somehow handle architecture as well. What is the scale of a unit? Are we talking about local scale, interpreting observations in core, which occurs here? Right, so the Atchafalaya delta is very much field-based. If you have a core through it, and if you interpret it as a fluvial dominated deltaic package, this is the scale you should be thinking of. Whereas the Volga delta might have a lot of stuff in it, which you'll never be able to infer directly from a single data point. So again, a second problem. First of all, processes can change across the same system. And secondary, we need to worry about different architectural scales within the same system to effectively handle them. So it is useful to be able to describe fluvial shallow marine depositional systems from this architectural standpoint. And this is where the wave process and architectural classification came along. Now, this was something which was public. I should mention that a lot of this work was also done by Bruce Ainsworth back in the day, who is currently at Santos. So a lot of these kind of conceptual models have very much been a team effort. So one thing that we can then do is, in terms of nomenclature, we just decided, let us make sure that we come up with a hierarchical frameworks of names. And let us make sure that we can kind of have this nested hierarchy of, for example, a TR sequence, and then a para sequence, and then a scale of a depositional system, scale of delta lobes, scales of facial associations, scales of heterogeneities. Now we use separate names, things such as RICAS, ECA, ECS, EC. Again, we wanted to make sure that our names do not get confused with anything else. But the idea is that we are using this framework. So if you're interested in something that occurs on a depositional system scale, you would go to, let's say, this level. If you're interested in what delta lobes are doing, you would go on this level. If you're interested in interpreting a facies association that you observe in core, you would always start at the facies association level. And you would then, as a later step, start asking questions about, okay, what type of depositional system might be occurring in such a setting. So we have this notion of an element complex assemblage. Now this is the level, you can think of it as the depositional system level. So this is the parent, the most useful parent unit if you want to think about regional scale architecture of a particular flavor. So notice that we have this hierarchy. So we have a TR sequence with a transgressive and regressive portion. The regressive portion in this case, let's say a para sequence, would be made up by more than one of these ECA units. More than one depositional system can occur within the same parent para sequence. And because those things are important, we have actually drawn up little kind of cartoons and icons of what they look like. So we want to differentiate the original fluvial dominated ECA. So our Volga example that we looked at and just a little bit was an example of this, versus what happens if we start adding additional processes. So how is an FECA system on a regional scale different from, let's say, an FW system versus an FTW system? Okay. So we have this way of differentiating and labeling things on a regional scale. Now, to give you just a visual of what those things mean, let us look again at the Danube Delta. About 6,000 years ago, the shoreline was outside of the map that we can see. So there was a big, basically funnel-shaped water body, sea level stabilized, and through time, the system started prograding until it's made its way to its present-day coastline position. So we're looking at 6,000 years of progradation in the Danube Delta. This is what we call, you can call this thing a parasequence. This is what we give it a different name, a recast. Now, the Danube Delta has this barrier island feature, which turns out to be quite important for what happens locally, depositionally within it. So everything seaward from this barrier island is impacted by waves. So in this case, we have a portion of the delta which is more wave dominated. So we would call this an WF ECA. But we also have a portion of the delta which is more fluvial dominated. Okay. So the point is that we don't want to be mixing this unit with this unit because it has very different features. It is made up by different phases associations. They are all part of the same parent unit, the same recast, the same parasequence, but we want to have a way of actually kind of figuring out the local flavor of the architecture, which is, for the most part, formed by the process regime locally that occurs at the shoreline. And we also want to be able to assign different names to what happens seaward from the shoreline. So first of all, here we are kind of in a funnel-shaped basin, so morphologically things are different, and also from a process standpoint we are in something which is entirely fluvial dominated, so yeah, very few waves would be able to go past the barrier island, which is protecting this area. So this is what, when we refer to ECA, these depositional system kind of parameters, this is what we refer to, parts of a system which have a given flavor in terms of what builds them, which is related to the regional process at the coastline. Now, inside, something else which is also important in the Danube is that the channels that are building the Danubes are evolving over time. So we have had 4 major evolutions, basically forming 4 big delta lobes. 3 of these delta lobes are forming more of kind of under a wave-dominated condition. One of them is more fluvial dominated. So notice that we have these delta lobes which are internal to our ECA units, internal to our depositional system scale unit. Again, sometimes these delta lobes can be very important in your reservoirs. They organize depositional systems within them, and sometimes this is something which you might want to capture in modeling. So the Danube system actually has 3 types of ECAs, and at least one of them has lobes internal to it. Okay, so then let us go one level up. So this is our regional system, the ECA unit. These are our lobes. Now, what happens inside of a lobe? Well, this is where our element complex unit comes in. Now, this is a very important unit because this is the unit you should always be using when you try to relate local observations in core and a depositional environment. So the point is that in this case, for example, imagine that we have a lobe which has more of a mouth bar portion, and then the bits adjacent to it, which are still part of the same 3D lobate figures. Imagine that we have 3 cores, wells which are penetrating this interval. They would see different things. So the faces in the mouth bar package would be different from the faces that you would observe, let's say, in a wave-dominated lobe package adjacent to it. So we should be very mindful of the fact that when we look at core, what we should try to identify is the name of one of these things. And then as a next step, we would actually go in and ask ourselves the question, okay, is this part of a delta lobe? What type of a parent depositional system can what we just observed occur in? And again, because those element complexes are fairly important, we have put in kind of drafted little cartoons that you would find throughout the database. So very often we will be using these visuals in the various modules that we use. So when we give you, let's say, a potential answer that something can be a fluvial dominated mouth bar, it will very much look like this. Okay. So again, be aware of the fact that we want to give one set of names to what we observe in core locally. This is our faces association. We are in a part of a delta lobe, which is wave dominated and tide influenced. versus what happens more regionally from a depositional system standpoint. Like we are in a part of a depositional system which contains delta lobes, which have a given process variability associated with them. So to get a feeling for what is meant by this lower scale kind of EC units, let us focus on this front part because it is the most straightforward. So as we mentioned, we have a number of lobes over here. Inside of each lobe, there will be a mouthbar portion. So these are our mouthbar element complexes. If we have a core through this interval, we would get, we can use faces to interpret a mouthbar depositional environment. Adjacent to that, we have these lobe EC units. Again, we assign those things a different name because the faces would be different. So we have these element complexes, which are part of delta lobes, which are part of larger scale depositional systems. Everything is named so that if you're interested on architecture at a specific scale, you can very much go to the right level of the hierarchy and be done with it. So just to kind of, you should think of those things as a tree. The entire Danube Delta is an example of a recast. So this is a parasequence basically. For 6,000 years, the shoreline has prograded until it's made its way to the present day coastline. Internal to these 6,000 years of progradation, there is regional variability in process. Everything is fluvial dominated behind the barrier. In front of the barrier, we have a more wave dominated portion and a more fluvial dominated portion. They are different enough to assign them different parent categories in essence. Inside of these ECAs, we can actually have delta lobes, which we call ECS, element complex sets. This is just you can think of a delta lobe as an internal reorganization of the depositional system on this scale. Delta lobes form when a channel evolves seaward from the landward from the shoreline. So you get a new point source at the shoreline, and which is allowing the depositional systems to build through time and do the thing that they do. Internal of a delta lobe, we have a number of element complexes. These are our facies associations. And as again, this is a very important point. When we look at core, we should always be asking ourselves the question, what type of a facies association are we in? Are we part of a WF lobe element complex, which is a wave-dominated package, part of a delta lobe, adjacent to a mouthbar deposit? Or are we part of a mouthbar deposit associated with the same delta lobe? The reason why this is important is because just because you make an observation of something being wave dominated, it does not mean that you're in a regional shore face deposit. Okay, so again, this is why we want to do this, because this is allowing us to study the complexity at the local scale, and then through parent-child relationship related to the complexity that occurs on a more regional scale. Now, sometimes a wave-dominated package in core would be formed in a regional strand plane setting where we don't have to worry about anything. That would probably be happening most often than not, but we should know that just because we see this in a single core, there is these other kind of alternatives which are also possible, which can give us very different fluid flow behavior from a reservoir standpoint. Okay, so imagine, so everything that we've talked about so far has been in plan view. Modern data is awesome for plan view. I always feel that we don't think about plan view enough in the ancient. Like, we are geologists, we tend to kind of live in this vertical cross-section world. Getting a feeling for what real depositional systems do in plan view is important. But of course, we should be able to relate the plan view to the cross-section as well. So imagine that in this case, we have some kind of a cross-section which is cutting through this entire parasequence. Now, what are some of the things which we might want to capture? And again, from a practical standpoint, from a modeling standpoint, this will very much depend on, what is the complexity of your reservoir, what type of fluids you're dealing with. Maybe for a gas field, complexity would not matter too much, but Sometimes it does, right? So we will be able to describe this unit kind of as a parasequence. So this entire package is part of a single parasequence. If we have a cross-section through it, we can lump everything together as a parasequence, what we call a recast. Now, in this particular case, this parasequence has these element sets as a part of it. So these are our delta lobes. Again, in some environment, delta lobes can be quite important. So these surfaces can be quite muddy. I mean, they can have very different flow properties. Everything is reorganizing in the delta lobe as well. So the directions of progression and all of these things would be changing along these surfaces. Sometimes they would matter, sometimes they would not matter. Again, this is more of a practical thing, but it is important for us to be able to go to the right scale and get the right data when this type of variability is important. And something else, which is mostly coming from the mouth bar work, both in outcrop that we did as part of the WAVE consortium, and both as in terms of this modern mapping, which was done more recently. Especially when we're dealing with more fluvial kind of dominated intervals and mouth bar dominated intervals for the most part. We also have to worry about what happens on this very local scale inside of the mouth bar element complex, where we can have these kind of low bait shapes, a lot of heterogeneities, a lot of variability, which again would have a very big impact on fluid flow once it occurs. Okay, so I think that this is all I had to say about architecture. Let me just have one final slide. So parasequence scale, delta lobe scale, mouth bar scale, all of these levels of heterogeneities can be important, kind of depending on the particulars of your field architecture and the fluids you're working with. So very often barriers and baffles would be occurring on these levels. So that is kind of the idea. So when this matters, we should have a way of describing it and capturing it, and we should not be confusing the architectures of these things. So again, one of the reasons why this process and architectural classification is very useful in practice is that when I call something a mouth bar element set, now this is a unit which falls even below the element complex, you would automatically know what I'm referring to. You would know that I'm referring to a detail of a part of a prograding mouth bar dominated package, most likely forming over several or 10 years of deposition. Having given scales, you know that this element set is part of a bigger package, which is the entire mouth bar package, and in turn you would know that the bigger mouth bar package is part of a delta lobe, which would be captured at this scale. So I guess the main point that I want to make about the architecture is that by using this terminology, and the databases use it internally. So if you want to effectively use the WAVE, you want to use Sedbase apps and databases, you have to be familiar with these terms. But also they're very practically useful because if you use them, there is very little confusion about the type of scale that you're referring to, the type of length of deposits that you're interested in, etc., etc. Okay, so this is kind of the end of the lecture portion of our first webinar. Just to give you a feeling for what will be happening next in the webinar series, I think that the next one is 2 weeks from now. I think that we have them scheduled every couple of weeks. The next webinar would be focusing entirely on the first part of the workflow, the classify part of the workflow. So we would see examples of what types of apps we have available that would help you relate observations in core to an interpretation of a faces association. We would then see how we can use these faces association interpretations to make predictions about what more kind of parent depositional systems might be occurring in. So this is the next webinar. So we would get to see all of the absent things that deal with interpreting core. Then we will then have a deep dive into fluvial dominated, wave dominated, and tide dominated environments, mostly kind of using our analog data as a guide. So this would these webinars would first of all teach us how to use the relevant modules in the database, but also would be kind of a nice introduction to these environments based on our somewhat unique data sets, because nobody has actually spent as much time mapping things as we have done in Sedbase. And then the last webinar in the series would focus more on channel data. As you were able to see, we have a lot of channel data in the database, so channel belts and channels. We have ways of seeing how those things are different in, tide dominate, wave dominate, fluvial dominate environment. So there is definitely enough material and sense to focus on channels specifically. Okay, so does anybody have any quick questions before we jump to the demo? If there is no questions, let me. Okay, so let us start off at the beginning. I'm not sure how many of you have not signed up to Sedbase yet, so let us actually go over that fairly quickly. To get to the website, you need to go to sedbase.com. This is our domain. You then click on the sign up button. I cannot demonstrate this at the moment. Hopefully I don't log myself out now. I don't want to sign out. Okay, let me leave this as this. So the point is that you would go there and you would this is the live demo gods. So you would follow a sign up procedure. And again, the key thing is using your company email. You would sign up. You would get an email from us with an authorization code. You would use it, and at this stage, you would always then use a sign in button, login button to get to the private page. Now, this is the private page. Again, for the first time, I would highly recommend actually going through some of these steps and becoming familiar with our documentation pages. So we have fairly kind of robust documentation now, which wasn't available before. So you should be aware of that. Something else which is new, and what I would actually be showcasing today, is we have a new module which has just turned live. Now this is very much in alpha version, so again, use with care. It is possible that we might run into bugs still. Things or when I use it, things seem to be working well. But again, be aware that every company is a bit different. Your computers are a bit different. I'm based in Europe. You're based in Australia. So be aware that it is possible that there might be some issues that are still resolved. But as you will be able to see, this is actually quite a powerful way of joining all of our modern data sets together. At the moment, we have all of the data sets minus the mouth bar portion. But again, let us actually see what this thing looks like. So at the moment, once you open, so once you click on this button, Integrated Modern Dashboard, a page would open up which has a number of components to it. Now, this is an example of a single page application. So most of the modern web applications that you use are built in that way. So we don't have separate pages anymore. Everything kind of seamlessly works together. Again, all of this makes the actual software side of things a bit more complicated. So that's why I'm saying that we are still removing a few bugs here and there, but for the most part, things work. So what type of data is available, first of all? And in this case, now you have the filters on the left-hand side, which are showing you 3 different categories: systems, channel belts, channels. The button which is shown in yellow is always the active thing that you're working on at the moment. So at the moment, we are in the filter part of the menu for systems. On the right-hand side, we have a display area. Okay, and this display area very much has to do with systems. Okay, so let us see how that works. We have filters on the left-hand side. We can select a particular system if we like to. We also can do a live search. So in this case, I put in the letters DAN. So I'm being given a list of systems which contain these characters within them. So if I click on Danube, notice that everything on the right-hand side, actually all of the systems disappeared, minus that one. So this is the Danube system. So notice how the map on the right-hand side is interactively responding to what we do on the left-hand side. Notice also that we have this kind of menu on top, which is giving us the number of active systems which are currently valid based on the query that we entered. Okay, so at the moment we have not selected any filter, so we have 336 systems which are active. Now let me say a few words about, before we get to the filters, let me say a few words about these live maps. You can do a number of things with them. We have these interactive menus now. So for example, each map would have a satellite view and a more of a relief-based view. So you can very easily toggle these on and off. So let us actually go to the relief-based view. We can completely remove the relief if we like to. Again, quite easily, interactively. Sometimes those things are useful because, for example, if you have selected something and if you cannot see where the polygon is on a map, removing the relief makes things a lot easier. We also have layers. Now, these are our geomorphological layers. It is that easy to be adding them and removing them. So now I'm taking out all of the beach ridges in the entire area. I'm taking out all of the channels. If we zoom into a particular system, this is the system polygon. So this is where we have defined the shape of the entire system as a whole. Now, something else that you can then do if you like to, you can actually change the visibility of the system itself. So if you want to see some geomorphological detail, again, you can very easily use this live map to be doing all of these things. Something else which you can then do is if you click on a system, a pop-up menu appears. Now this is a live map. So this allows you to very quickly kind of get a feeling for what a system looks like. If you click on this icon on the top right, you actually get to see the same system in kind of bigger view. Now I'm still limiting the size of these pop-up windows at the moment because I'm noticing that with older computers, a lot of these maps are quite, they demand a lot from the browser, and I've run into issues on older machines. So at the moment, the sizes of things are not as big as they can be, but again, we don't want to crash your browser. So again, be aware that we have all of this interactivity directly built in. So we have a way of looking at systems. Let us turn on back the satellite view. Now, let us say a few more words about filters. So one thing that then happens every time you apply a filter in the background, we connect to our database and it gives back the relative data. So if I call, for example, if I click now on Fluvial, you will see that a lot of our systems disappeared and only systems shown in brown are shown at the moment. Let me actually zoom out so that we can see more of these things. If I click on tides, only orange systems appear. So these are our tide-dominated systems. If I click on wave, only wave-dominated systems appear. Okay, so you can very easily and quickly narrow down your search in terms of process. Now we discussed that process is a fairly important thing. Going even further, one thing that you can then do is you can actually use these more precise process categories. So at the moment we are under a wave-dominated setting, but you can use these more precise process categories to further refine your search. So if you're interested in wave-dominated fluvial influence systems without tides, if you click on the WF button, you would notice that some systems that were on the bottom disappear, right? So this is a Niger Delta, it is tide influenced. If you click WF, it is gone. So you can select as many of these buttons as you like. So the point is that you can quite easily refine your search in terms of the process that you're interested in. Now comes probably the most useful part of the entire app. If you click on this button, now we have applied a filter. Fluvial, we have our filter is wave dominated, and more specifically wave dominated fluvial influence, WF. Now in this case, you see all of the examples that we have in the database which fit this category. I'm just scrolling my mouse down. I can get all the way through the list. Now this is a big improvement over what we had before. So it is very easy for you to get, very quick visuals for a particular query that kind of gives you a very quick view of what a system looks like. At all cases, you can again go in, zoom in, and study a system in detail. All of these maps have all of the layers and filters activated. So again, we can very easily, tilt things, change satellite to relief view, etc., etc. And something else which is very neat is that the next thing that you can then do, we have added this check. When I say we, I should say I, because I did all of this work. So what has been added is the ability to actually select systems interactively. So in this case, let's say that we're looking through these systems and I'm saying, okay, so the Danube seems like a good analog. Let me say, for example, I like this one. So I would include the Frontera system. I would include Rio Coco. I'm scrolling down. Okay, I like the post system. So I'm including the post system. So notice that because we have hundreds of systems, you can actually go through them. You can select the ones that you like. You can only show these then, if you like to. So again, this is a very quick way of figuring out what analogs you want to work with. Yep, so this is one capability. Something else that we can then use is we have these sort menus. So at the moment, maps are shown on a category which I call map quality, which means better analogs visually, kind of with more data, etc., come first. But we can also use, for example, fluvial gradient. Now, the fluvial gradient in this case is actually going from high gradient to low gradient. I can very quickly reverse this. So I have this sorting menu. So right now we're looking at fluvial dominated wave influence systems going from low gradient to high gradient. Again, if depending on what type of system you're working with, this is very, very powerful, because one of the variables that we will be discussing a fair bit once we start talking about analogs, it turns out that the stream gradient of systems is a very big thing that you have to worry about in an ancient setting. So systems such as the Danube, which are formed by big rivers under low gradient conditions, are behaving very differently from other systems which are under high gradient. Channels are a lot more unstable. Things are migrating a whole lot. You end up getting very different architecture. Okay, and the last thing that I should point out is that now we selected 4 systems. We viewed them, which is fine, but in fact, these 4 systems are still selected. So if you want to select a particular system, and then if you want to see what data we have available for it, it is very easy to directly do this using the map view. Now, of course, you could have done this all along using this system selection check marks, but again, working with the visuals is a lot more powerful in this case. So to deselect everything, and so notice that we only have 4 out of 336 systems selected at the moment. Now to go back to the original view, all I need to do is to refresh the system view. So we go back to wave-dominated fluvial system, WF systems in this case. So notice how, because this is a single app application, all of this interaction is fairly straightforward. Before, everything was done based on separate pages. So you would load one page and then another page, whereas now, it's as long as things are programmed correctly, which is not very easy, admittedly. But once they start working together, it becomes very easy to be jumping between views, filtering things interactively, etc., etc. So in this case, we have deselected this. Let us change the dominant process to fluvial. So I need to deselect this as well. Okay, so did you notice what just happened? I put in Fluvial, WF was still selected, and there is obviously no systems in the database which are Fluvial dominated and yet have a WF as a process. You know, one of them is wave dominated, one of them is Fluvial dominated. So the system basically says that there is no such systems which are available. So right now we select Fluvial dominated. Again, we can view this thing. So this is our so right now we are working at the system level. And here comes the neat thing. If I actually scroll down, and if I select channel belt, now I go to the channel belt dataset. Now before this was a separate app. Okay, but now we are still in the same app. We still have all of the filters for systems applied. So everything here is, so we're still only looking at Fluvial dominated systems, and therefore channel belts from Fluvial dominated systems. So we can actually go in. Now we have just a bit over 1,000 channel belts under this category. So we can zoom in. All of these are live maps. We can change all of the controls that we were discussing before. You know, we can make things less visible, invisible if we like to. Now, another feature which is neat, which was added, you can actually make those things 3D from a visualization standpoint. Again, I find this like it helps me for whatever reason to think about, you know, channel belts as three-dimensional geobodies versus just a polygon on a map. Again, you can toggle those things on and off. So this is the visual side of things. But the neat thing, which is something which wasn't available before, is that if we scroll down, we now actually have live charts which are being generated depending on the filters on the left-hand side. For example, in this case, we have median channel belt width, maximum channel belt width, channel belt sinuosity. We have actually a measurement of how curved is the outer surface of the channel belt. So in all of these cases, we can actually go in. So if we click on kind of this model pop-up item, we can actually see the data being shown. Again, interactively, we have stats on top. We have a capability of limiting the data that is being showed. And we also have these live ways of interacting the data. So for example, in this case, if I put in 0.1, I've selected a new bin range. We can very easily kind of change the data in the histogram. So be aware of that. We can also use numbers of histograms. So if I put in 50, in this case, we split up the system as 50. If I put in 100, here is 10, here is 100. So the point is that you can very easily kind of interact with these charts. We also have a cumulative frequency graph shown on the same map. If we scroll down, we also have cross plots. Again, we can very easily examine this in detail. But one more thing that I should mention is that all of these charts, so in this case, I've selected to show you a few charts just as a quick guide, but all of these charts can also be obtained from a particular filter. So for example, if I would go to average LD, remember LD was the direct distance between two inflection points. If I go to cross plot, I can select what I want cross plotted. So for example, if I generate a cross plot of the average LD versus the average distance between the local width minima of the channel belt, again, I get a relationship. If I do the median width of a channel, again, I get a relationship. There is supposed to be a line of best fit in a lot of these charts. It sometimes appears and sometimes disappears. I still have not figured out what exactly happens there, but the point is that once this bug is removed, you would also get kind of a feeling for the correlation. The stats of this is always given to you. So in this case, we have a correlation coefficient of 0.75. R squared is 0.56. So notice how we went from systems to channel belts quite easily. Let us then go to channels. So if I would click on this channel button, now we would switch to the channel data set. So notice we have a new map. Our system selection is still active. So we are still under Fluvial dominated setting. Our map view is showing us, let me actually remove some of the geomorphology so we can see things better. So in this case, you can see where the maps are, where systems with channels are around the world quite easily. Once again, if we scroll down, we get a kind of a number of live charts based on what we just put in. So in this case, for example, let us focus on this one. This is showing us the maximum depth measurements of channel points. Okay. So in this case, as you can see, we have a number of these, and this is telling us that for a Fluvial dominated system, we have a range of channel depths that might occur. But the neat thing is that we are at the moment under this channel view, but we can still apply system filters to everything. So the different data sets are talking to one another. So in this case, if we are interested, let's say that we are actually seeing tidal influence in our systems as well. Let us see what the effect is of tidal range. So in this case, we are still under Fluvial dominated. Let me actually, maybe, yeah, we don't have Fluvial dominated tidal channels, of course. So let me deselect that. Okay, so now we get, for example, we get a feeling for the depth range of mesotidal channels under mesotidal settings. So this is tidal range between 2 and 4 meters. If we click on macrotidal, you can see that these numbers change. Channel depths are actually getting bigger. If we click on macrotidal, we have fewer points here, but you can see that some of the channel depths can get quite significant. So we have many things that are over 20 meters. So notice how everything is working. Again, we will be playing a lot with this module once we start talking about our Fluvial dominated, wave dominated, and tide dominated webinars. Be aware that this is available to you now. Please let me know if you run into any bugs. Again, with these things, everything. I typically use a Mac. Everything works perfectly on it. I tried it on an old PC. I ran into some issues. I fixed them, but again, every computer is a bit different. So please let me know if something is not working out for you, so that some of these errors can be resolved. The plan is to have the mouth bar data set added as well, and all of the bugs removed in the next couple of months. All of the old modules are still available. They will be available for 3 more months. So in a way, they would be deprecated, and then this thing would pretty much be taken over. I'm sure that you would agree this is a much more powerful approach. So it becomes very easy to relate. You can also relate channel belts to child channels as well. So in terms of queries, this is a lot more useful, I find. So I think that this is all I want to say today in terms of the live demo. Again, the last thing which I should have done was to, if we actually go to the Wave knowledge base main page. Again, this is the main page. Next time when we look at Classify, we will be using a lot of these modules. So if you click on these buttons, you would see what is available. We have atlases. So for example, these are the old versions of the atlases. So if you click on the Modern Delta Coastline Interactive Atlas, you will see the old version of the atlas that dealt with systems. The new atlas has also been incorporated here. And again, notice this is an alpha version. So again, please don't blame me too much if something goes wrong. Typically, if something goes wrong, if you simply refresh the browser, it fixes things. But again, please let me know if there are some issues. Okay, so I'm stopping sharing. Does anybody have any questions? Unfortunately, it's almost the top of the hour. I'm happy to hang around longer if you want to. I should have left a bit more time for questions. Does anybody have any quick questions?
I'll kick it off, Boyan, if that's all right. Fantastic improvements. I think it's looking you know, a lot cleaner, and it's great to have all those atlases together. That's a really big improvement. Quick question I had for you: with the mouth bars, is the intention to get the mouth bar elements, individual mouth bar element data in there as well, or is it just going to be the mouth bar complex?
Yes, so for now it will be the mouth bar complex. I mean, the plan is down the line to add the element sets as well and the elements.
Okay, great, because that'd be really useful to get
Yeah,
that data.
yeah, for sure.
Yeah.
Yeah. Is there any other questions? And please let me know if everything worked well with the Teams webinar. This is actually the first time I've used this. I use Teams a lot, but I've never used the webinar. So please let me know if you were able to hear me, if there was any technical issues, if you're happy with the format. It doesn't fortunately require you to have to register for every webinar, but I think that it's a fairly straightforward process. Also, the webinar is being recorded, so I would see how I give it to you. I would most likely end up posting it on the website, but again, this should be available to you in the next couple of days.
It all went well.
Yeah, perfect.
Thank you.
Yeah.
Okay, so
Thanks
if
for
there
that,
is no,
Boyan.
yeah, so if there is no more questions, I guess we would. The next webinar would be 2 weeks from now, same time. Again, pretty much following the same format. Let me know if you're happy with the format as well. I mean, I've decided not to include exercises, but I think that there is a lot of material to go through, and this probably would work better as a webinar format. But please let me know if you're happy with the format and if you would require or would prefer to have some changes. Again, I'm quite flexible. So if there is no more question, it's the top of the hour. So let us finish things off. So thank you everybody for attending, and see you again in 2 weeks.
Yep.
Thanks,
Thank
Boyan.
you.
Bye-bye.
Thanks, Boyan.
Hey, thanks, Boyan. See you.
Stopping
Yep.
the recording.
Bye.